Our next talk will be given by Caitlin Ahrens, presenting work by herself and Noah Petterall. And it's titled Shedding Light on the Darkness, Diversity of Permanently Shadowed Regions at the Lunar South Pole. Take it away, Caitlin.
Thank you so much. All right. So, if I were to describe to you how in the world do we actually classify PSRs, in my analogy, I kind of consider it as like if I were to give you a rock, would you describe it as what's the grain size of it? Maybe how heavy is it? How does it smell? How does it taste? We all have classifications for something. We're all geologists, or most of us are geologists here, and we love to classify something. And so when it comes to figuring out what in the world these permanently shadowed regions are, we've kind of gotten into this overall sense of, oh, it's just water ice, it's just volatile ice. So in this case, not necessarily the case here, though. So really brief overview, though, these are just really, really, really cold spots. They will be somewhat have variations in seasonal temperatures, typically below 110 Kelvin, but some areas can go up to at least 250 Kelvin and then all the way down to 30 Kelvin. So huge swath of temperatures, but I'll get to as to why that's actually very interesting here in a bit. As our previous presenter just made ourselves aware of, is illumination is also something to be aware of with these PSRs. In that case, the topography would also play a role as to how are these PSRs even accumulated and crystallized. So it's not just temperature variations, it's also just all this accumulation of these different kinds of volatiles. So these are just very open questions. We're not going to be able to answer these right off the bat. These are very, very simple questions, but with very complex means of answering them. So how are these volatiles formed? What kind of volatiles are we dealing with? And then looking down at the grain size scale of these PSRs, the crystalline structures, the sublimation versus the accretion. So all comes down to location, location, location. Now, granted, this entire session is the south polar region of the moon. Okay, great. But what I mean by location, location, location is where are the volatiles in relation to their crater? Are they completely enveloped into the crater? Are they more maybe on the wall? Are they on the wall and the floor? So where are they located within the crater? And that's what I'm meaning here. So taking a look at certainly with WAC and NAC imaging, LOLA, and then also Diviner is also a huge help here as well with the glorious temperatures as well. So we get this beautiful Diviner data with the bolometric temperatures that you see at the top here. So you might just see like, okay, there's a lot of blue and purple here. That's great. There's a lot of cold spots. But now then it comes time to, it's not just water ice anymore. So these are about the maximum temperatures that some of these volatiles would be frozen at. And so it's, again, not just water ice. It's so fascinating. You can have sulfur types of volatiles, CO2, ammonia, and then getting into hydrogen sulfide and sulfur dioxides. Julie Mitchell is actually doing some amazing work with these types of volatiles as well, and her and I have been chatting a lot on these types of different kinds of fun ices. So in its complete barest sense, types A, B, and C, and D, I know, we're so original. But if we were to just go completely by location, it does not tell us the full story at all. So in that case, how about the size? What can we do about the size? How is the size of the PSR related to the size of its crater? Well, okay, there could be some minor relationships here, though, with some dots potentially overlapping here. So let's dig deeper then. Yep, so there's our crater ratio. Going deeper then, how about the slope? At what angle are some of these PSRs even located with means of their crater? So thank you, Miriam, Lemelin, if you are listening, and thank you for your slope angles in your latest 2021 paper. That has actually been a huge help. So in that case, looking at the slopes and how those slopes may have affected some of the accumulation effects of these PSRs. Yeah, okay, now we could start to see some of those distinctions, but there's more. Yep, so there's their slope differences. Now we want to see, how about temperature? How do all of these different types have to do with different kinds of temperature, though? So looking at the max summer temperature, a good portion of these are well into the water ice, maybe a little bit of the methanol, not so much at the more exotic ices until you get into your winter temperatures. Now you start to get into all the really pretty exotic ices there. The little ellipse that I have here is the type C and D. A bulk of them happen to be just around the methanol water ice regions, not necessarily the exotic ice. So that's something to look into very shortly. So then if we were to just look at the temperature difference, your summer and winter, or maybe your summer maximum and summer minimum, how much of a temperature range do you get? Because the larger the temperature range, the more your crystallinity is going to be very unstable. So with all of these combined, now we can have a better sense of what the different types are with these PSRs. So a very basic map that Noah and I are working on right now. Really pretty color coding there and whatnot. But then real quick, how about the height at which these PSRs are found within their crater versus the length? How far into the crater are some of these found? So this is something called the HL ratio. That I myself have done with volatiles on series before. So if we use the kind of the same technique here, this ratio can certainly be not so much of the friction of the ice, but so much as the crystallization of the ice. In which case there is no relationship here, and actually that tells us a lot because there's it just looks like a complete mess right now. What this means is that the grain boundary at the crater wall or the floor is actually affecting how it's being accumulated. In which case, the PSR itself is actually not homogeneous. It's not just a water cube, a water ice cube or anything. It's very crystallized. Yes, so that's pretty much what I just said there. So why have a classification? Good for us, it's type A, B, and C, and D. But in reality, knowing the different kinds of crystallization types and knowing the different kinds of thermal variations that we can have can really help us out with further exploration, especially with Trailblazer and Viper, eventually to Artemis, figure out like, okay, where are the pure water ice water spots, and then where's the carbon dioxide spots, and then also where's the ices that you want to be really careful of, especially the hydrogen sulfide type ices. So there's always sorts of fun ice exploration, but then there's some safety and hazards. But also I answer at the very bottom, why not? Just why not? So I'll leave it to this slide again as to the open questions regarding PSRs, whether this includes the classification or not. But we should probably better understand just the crystallization and just the grain physics of these PSRs further. And that's my talk, so thank you so much.
Thank you so much, Caitlin. We have a question in the chat window from incomparable Jennifer Hellman. To what resolution are you assessing minimum maximum temperatures across a PSR? Within any PSR, there can be variability in temperature as a function of location within a PSR. What is the level of detail that you can assess in that range?
Very good question. So I'm mainly looking at diviner resolutions here. So granted, diviner is not like complete spot on or anything though, but I am not looking at average diviner temperatures either. So I'm going back through the archives and looking at how the temperatures vary from year to year, as well as good as coverage as it can be. But once hopefully Trailblazer and Viper get there, then we'll have some hopefully some higher resolution thermal data there.
I think also there's a scale resolution as well. For a large PSR, you may have a single point that has, defines a minimum maximum for a larger area. So how do we account for variability within a PSR as well, beyond just the range at any one point in time? That might be the question, but we can follow up in the chat and certainly during the discussion later, but you may want to follow up with Jen Heldman in the chat window.
Great, thank you.
Thank you.